Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Okay, now we'll come to solid solution strengthening with a specific idea. We just looked at it in a general formulation about an obstacle in a matrix in the initial slides, but now we'll talk very specific systems. So here is the schematic which has the lattice, and some of the lattice positions are substituted by the foreign atoms, so-called substitutional solid solutions. And then you see that the black ones and the open circle, they are of similar size, but here you are also having a solute atom which is smaller in size as compared to the rest. Okay, so what you see here is the slip plane, and then this kind of this is a void, and this could be a edge dislocation, something like that, and the direction of the dislocation motion is this way, and then this is slip direction. All this you understand now. So now the question is, having the small solute atom in this position, what are all the consequences? This is what we have to understand. So now you know what kind of a stress field surrounding an edge dislocation. We have sufficient idea. And when the solute atom is small as compared to the solvent atom, then what are all the consequences? An edge dislocation moving on a slip plane containing a solute atom of a diameter of atomic size less than the solvent. When the dislocation core reaches the solute, the compressive strain energy, that is somewhat relieved. So what is that we have seen in the dislocation core? Above the extra half plane, especially the hydrostatic compression, that is what we have seen. So the compressive strain energy is somewhat relieved when the small solute atom goes and get locked inside the dislocation core. This leads to an attractive interaction energy between the solute and the dislocation. This we have already seen. If the solute atom were positioned below the glide plane, a repulsive energy would result. Okay, so this scenario is quite interesting. Now, a small solute atom, we are putting the dislocation core above the glide plane, then it becomes, kind of attractive forces, attractive interaction energy. The same solute were positioned below this, it's a repulsive, because the stress field is quite different. It is tensile, hydrostatic tension, right? It's a repulsive. Thus, a small solute atom can, depending on its position relative to the glide plane, attract or repel an edge dislocation. Okay. A similar result is obtained when the solute atom has the size larger than the solvent. Okay. So we are now generally talking about size effect here. Okay. On the average, both relatively larger and smaller solute atoms interact attractively with an edge dislocation, and an increase in the flow stress results. Okay. So whether it is a larger or smaller, the net result is the increase in the flow stress. That is important. Okay. Now we are going to look at little more closely. These two plots exhibits comparison of the strains associated with spherical or tetragonal distortions. Okay, what is spherical distortion? What is tetragonal distortion? We can spend some time on this. I said that if you bring a foreign atom to a matrix, especially in this case, we are talking about a substitutional solid solution. Suppose the atom of similar size, for example, in this case, the open circle and the black circles, they are of the same diameter. So what you have to understand is the diameter of the solute atom, even though it is comparable in size, they will not be exactly the same. They will produce some kind of distortion. Okay, but if it is of a similar size, then the stress field around is going to be symmetrical. Okay, it is going to produce symmetrical stress field. Okay. On the other hand, if it is a small, and it is not going to produce a symmetrical stress field around. This is what we are going to see. Okay, so that is what shown in this plot. A spherical distortion produces a dilation for which epsilon 1, epsilon 2, epsilon 3, they are all same. What is epsilon 1? They are all strain components. Strain components of 3. All the 3 strain components will be equal if it is a spherical distortion. Okay. For the tetragonal distortion, an octant of ellipsoid of revolution is formed. So this is what is shown. An octant of ellipsoid of a revolution is formed here. At what condition? That could be epsilon 1 is greater than 0, epsilon 2 and epsilon 3 is less than 0, or epsilon 1 can be less than 0 and epsilon 2 is equal to epsilon 3, which is greater than 0. That means one strain will be having a different magnitude than the other two, but the other two will have equal magnitude. That's what it means, the tetragonal distortion. Okay, so now I said that the spherical distortion comes when you have the substitutional solid solution. For example, if you take chromium in iron, or nickel in iron, or chromium in nickel. These are all some of the classical examples where the substitutional solid solution will experience spherical stress field. Okay, and then when will you have a tetragonal distortion? So before even going to the solute, if you compare the dislocation itself, the screw dislocation is completely associated with shear stress alone. Okay, so shear stress will be associated with some distorted bonds, which is also creates a tetragonal distortions. Okay. On the other hand, in edge dislocation, we know both it has got distortions as well as dilatation or dilation components. Okay, the shear stress as well as normal stress. But as far as the screw dislocations are concerned, it has got only shear stress. That means it's only a distorted, I would say, distorted energy or a distorted bonds. You can say, okay, distortion, tetragonal distortions. Okay, tetragonal distortions in the lattice will significantly interact with screw dislocations because of this, because of the shear stress. Some examples we are going to see now one by one. The first one shows the BCC lattice, which is going to exhibit a tetragonal distortion. So an interstitial atom in a BCC lattice, and B is a divalent ion plus positive ion vacancy in a monovalent ionic solid. So the matrix is monovalent, and you have a divalent substitution and a vacancy here. So this kind of imbalanced charge distribution is going to cause tetragonal distortion. And here we are talking about an interstitial atom which is going to sit in an octahedral void in a BCC lattice is also going to cause tetragonal distortion. Okay, so we were talking about the dislocation and its stress field and distortion, and then now we are talking about the lattice which is having tetragonal distortions. So you have to be clear about this. So only whichever the interaction is going to make a significant effect is all depending upon what kind of distortion and what kind of a stress field in both sides. So in the first one, that is the interstitial atom does not fit without a distortion in the structure, and this results in displacement of a solvent atom along the z-axis, that is tetragonal distortion results. In the example B, the divalent ion and the associated vacancy relax by approaching each other. This also produces tetragonal distortion. Okay. The arrows indicate the direction in which the atoms or ions move in response to the presence of distorting agent. Okay, distorting agent. Okay. So this is one simple demonstration about this distortion. Now I'll show a little more explanation on this with a few more examples. What is shown in this slide is first of all, the top image shows the resolution of shear stress into normal stress components. Okay. Since we are going to talk about the stress field around the dislocations and the other solute atom stress fields, this is quite significant. So you know this, the shear stress can be resolved in terms of normal stress. Remember, the magnitude of both shear and normal stress is going to be same. Okay, whether it is tension and compression. So the magnitude of all the three stresses are going to be same. Okay. So when you have this shear stress, for example, in screw dislocations, and there we can consider this is getting decomposed into these kind of normal stress components, and this will have interaction with the lattice energy now. Okay, lattice stress fields. Okay, so now we look at the first one, a non-symmetrical stress fields in the crystals. First one is octahedral interstitial site in BCC crystal. They will have anisotropy in 100 direction. Okay, so here we are going to this arrow direction, you can see, and what is shown here is the interstitial site. There are two possibilities. One is in the edge center, the other is in the face center. Okay, in a BCC lattice. Both of them are octahedral sites. The question is whether these octahedral sites are of similar size or not. They are not. The one which is in the edge is typically in the order of 0.038 nanometer. The one which is there in the face center is in the order of 0.156 nanometer. And they have the anisotropy in 100 direction as well as 110 direction respectively. Okay, we have not shown the other one, but there is an anisotropy in these two octahedral voids itself. So when you have this kind of anisotropy in the void size itself, when the interstitial solute like carbon, which is when it approaches here, their attraction will be very strong, because the tetragonal distortion, okay, which is getting generated in this BCC lattice is quite large, and that stress field are going to attract this interstitial carbon atom into this octahedral voids. Okay, and if you look at the carbon atom size, which is about 0.154 nanometers, and they are going to try to occupy into this octahedral site, which is not very convenient, right, to fill in, right? So that is why the the solubility of carbon in BCC iron is very low, 0.02%. Right? On the other hand, if you look at that the solubility in an FCC iron, it is enormous. So if you look at the void size which is there in the FCC, it is equal to 0.1 to 0.102 nanometers, which is much larger than this octahedral void, where the carbon dissolves, because the stress field there, it's not like a distorted one or asymmetric, it is a spherical stress field there. So the carbon dissolution is more when compared to the BCC lattice. So that is it has got a enormous technological importance. That's why steel is becoming very popular and still an important material. All of you know this, and it's a very classical example of having a distorted lattice but still forming a very strong solid solution. Okay, so non-symmetrical stress field in this BCC lattice, carbon as an interstitial is a classical example. So they exhibit anisotropy in 100 and 110 also. And if you take the second one, the divalent ion vacancy pair. So this is again showed in the previous slide, and it shows the anisotropy in 110 direction. Okay, and here again interstitial pair in FCC crystal exhibits anisotropy in 100 direction. Also will produce some kind of a distortion, and finally the vacancy disk exhibits anisotropy in 111 direction. Also will create non-symmetrical stress fields. So these are all some of the classical examples of how the crystal system will have non-symmetrical stress fields and how they are going to interact with the stress fields of the dislocation as the profound influence. So what we are now seeing here is energy versus position plot, where the dislocation is approaching a soft atom as a solute atom in a solvent matrix. Okay, so what you are seeing here is this is a dislocation and this is a position, and it moves this direction. And what you are seeing here is the energy of modulus, how it varies with the dislocation position, the energy variation. Okay, we were just looking at the modulus, and suppose if you look at the size, and if you look at the size plus modulus, how they are going to compare in terms of energy. So what do we say? Why do we say soft? Because if you consider the modulus of the solute atom is, is less than the solvent atom, so then it is considered as soft, and then that energy is going to vary like this with respect to the position of the edge dislocation. So if the soft atom of a given size, suppose it's a small size, and they are going to reinforce each other, okay, and their force versus position. So this kind of energy and force plots are quite familiar to us. We looked at in quantum Morse curve, right? So energy versus position and then force versus position. It's the same idea here. So if you have the a soft atom and a small size, they are going to vary. The energy is going to vary like this, and they are going to reinforce the energy, and then this is simply a derivative of this reinforced curve. So it is going to have attractive and repulsive or positive or negative force depending upon the positions for the soft atom. On the other hand, if you plot it for a hard atom, that is the solute atom has got the higher modulus than the solvent, then it is going to be, the energy variation is going to be like this with respect to the dislocation position, and the size is same. It is just that the modulus is higher than the solvent for a given size. But if you look at the net, that is energy of size plus modulus is becoming smaller. But in this, the previous case, it was a softer atom and a smaller size. The energy is reinforcing, but in the higher modulus and smaller size, then the net force is very small as compared to the soft atom. Okay, in terms of attraction as well as repulsion. So that means a soft atom with a smaller size will have strong interaction energy or a strong force with a dislocation. That is how you should look at it. Okay. So the interaction energy versus relative slip plane position of an edge dislocation is shown as a soft solute and hard solute. For the soft solute, the size and interaction energy is reinforced. This is not the for the hard atom, so it is quite different. So the size interaction is taken as the more important one, and this results in the net attraction between the dislocation and the solute. So even though the energy of high modulus solute and size varies like this, but the net is still attractive. The interaction force position relationship for these repulsive, respective cases is shown in C and D, so that we already seen. The force proportional to the derivative of the energy position curve is negative or attractive as the dislocation approaches the solute atom for both situations. The force necessary to continue dislocation motion, that is F max, is that required to tear the dislocation away from the solute. Okay, so we are now talking about the interaction energy of the solute with respect to dislocation position. That means their interaction, they are interacting, they are holding together, whatever happens. But if you look at the force necessary to continue the dislocation, if the dislocation has to continue to move, surpassing these obstacles, then that force has to tear the dislocation away from the solute. So that is F max should be high enough, whether it is a soft or a hard or whatever may be the case. If the dislocation has to move from this obstacle, F max should be higher. As a result of the adding of the size and modulus effect, this force is greater for the soft atom. Very important idea. So we are talking about strengthening mechanism. So that means this gives a clear idea. If you add a soft atom to the solvent, that is going to result in a F max is higher. Okay, you are going to require higher F max, higher force to move the dislocation. Both size and modulus effects produce a dislocation solute atom interaction energy that is elastic in nature. Please once again understand, we are still talking about elastic energy. Okay, we are talking about elastic, all the forces are still in elastic in nature. Okay. So we will compare the similar situation, that is the dislocation solute atom interaction energy versus position for a hard atom for which the modulus interaction energy has greater magnitude than the size interaction energy. Now, earlier we have looked at a moderate modulus interaction energy. Now it is significantly hard, okay, significantly higher modulus interaction energy with a hard particle. So this is higher interaction energy, but keep the size same, and then what kind of the force position plot will come is shown here. So the net positive energy results in the force position term. So this is a net positive energy. Here the force F max required to continue the dislocation motion is that necessary to push the dislocation by, rather than the, as the case of the negative interaction energy, the force required to pull the dislocation away from the solute atom. Okay. Here slightly different. There we said that tear away. Here it is kind of a push. We require little slightly in opposite sense. Okay. The dislocation motion to be continued, and the necessary force is to push the dislocation, okay, by the solute atom. The solute atom is supposed to push the solute dislocation to move away from this, or keep the dislocation motion in continuation. Strengthening results regardless of whether the solute atom dislocation interaction is attractive or repulsive. Very, very important point. We are looking at very closely whether it is attractive or repulsive depending upon the dislocation configuration as well as the type of solute and its size and its modulus. Okay. Ultimately, it is going to produce whether it's going to get attracted towards dislocation or it's going to repel the dislocation. So the net energy, whatever is going to result out of this interaction, is going to be beneficial for the strengthening of the material. That is the information. Okay. Okay, we will stop here. We will continue the lecture in the next class.